Alright, hi. So our group project dealt with Chapter 7 and Section 8.1. So the topics that we're going to be covering in this are methods of integration, which include integration formulas, integration by parts, trigonometric identities, trigonometric substitution, partial fraction decomposition, improper integrals, as well as arc length. And so let's dive right into it. The first things we're going to talk about are integration formulas. These are things that we really need to memorize and will save us a lot of time in the future when we're solving more complex integrals. Things like the integral of e to the x is e to the x. All of our trig identities are very important to know as well. The integral of a to the x is a to the x divided by ln a. 1 over x goes to ln x. Things like that. There are some more complicated ones down here like 17 and 18, which deal with inverse trig, and we should be familiar with these as well. So what we're doing in this example is we're trying to turn this into something that looks like one of our formulas, so we have an easy way to integrate it. So what we start off with is this integral 5 divided by 5x root 25x squared minus 16. From this 25x squared minus 16, we can mess around and change some things around. So we have 5x quantity squared minus 4 squared, and we have our x, which in this case is x squared, and a, which is in this case 4 squared. From here, this looks like one of our formulas for secant inverse, and because we memorized that, we can jump right to it and end up with 1/4 secant inverse 5x over 4 plus c. So the next topic we're going to talk about is integration by parts, which is applicable to most problems. The formula right here is the integral of u dv equals u times v minus the integral of v du. And this is very useful if you have repeating or alternating derivatives like e to the x or sine x or cosine x, something like that. Alright, so we want to find another integral right here, secant cubed x. And so what we're going to do is try and break this into something that we can use integration by parts for. So we have secant squared x times secant x, which makes sense. We can find our u, which is secant x, our du, which is secant x tangent x, our dv, which is secant squared x, and our v, which is tangent x. So we have secant x times tangent x, right, u times v, minus the integral of secant x times tangent squared x, which is, as we can see, v du. And from there, we can use our trig identities to see that tangent squared x equals secant squared x minus 1. Once again, from that, once we multiply the secant x on the outside through all of that, we can break it up even further into secant cubed x again minus secant x. And since all of this must be equal to the integral of secant x cubed right here, we can bring this secant cubed x over to the other side and have 2 times the integral of secant cubed x and have that equal everything else. So secant x times tangent x plus the integral of secant x, which is natural log of the absolute value secant x plus tangent x. And see, once we do this, all we have to do is divide by 2 to figure out what secant cubed x is. Our next method is the most subjective method because there's multiple ways to solve these problems. Trigonometric integrals are what we use when the problem contains trig functions to powers or multiple trig functions. There's a really big focus on the use of trig identities and power reducing formulas, because ultimately what we want to do is turn this into something that's nice and simple that works with one of our memorized formulas. So let's look at one example of this. We have the integral of 1 over cosine squared x minus 1. And what we want to do is turn this into something nice that we can make an easy integral out of, right? So we have cosine squared x, and that can turn into 1 minus sine squared of x, all minus 1, and these 1's cancel out, so we have the integral of 1 over negative sine squared of x, which turns into negative cosecant squared of x. And from that, that's an easy one that we've memorized, cotangent x. So our next method that we're going to talk about is trigonometric substitution, which is a bit more challenging. It's what we use when the problem has difficult radicals in it. We're looking again for these a squared plus x squareds that we talked about earlier on. It's very helpful to draw out the triangle to help visualize what's going on. A let box is very helpful also in staying organized here. We have the integral of x cubed times the square root of 16 minus x squared. What we want to do is let x equal 4 sine theta, right? We have sine theta equals x over 4, right? Opposite over hypotenuse. And we also want our dx to equal 4 cosine theta d theta. And we have x cubed, which based off of this x equals 4 sine theta, we have 64 sine cubed theta. And that's going to be what goes up here in place of x cubed. And we can see this 4 cosine theta also equals the square root of 16 minus x squared. And so all of this eventually we're going to replace our x's with these trig functions. And so what we're going to have is sine cubed of theta times cosine squared d theta, right? Because we're replacing our dx with 4 cosine theta d theta. And we're replacing this square root of 16 minus x squared with 4 cosine theta. And all of this is going to be multiplied by 1024 because we have 4 times 64. And then we're going to use what we have to break it up into things that we know how to solve. We can have a sine squared theta all times sine theta times cosine squared theta, which ends up being 1 minus cosine squared theta all times that other stuff. We have 1024, the integral of cosine squared theta minus cosine to the 4th theta, all times sine theta, when we multiply that through. And from here we can use a u sub, because we have, if u is equal to cosine theta, we have du is equal to negative sine theta d theta. That works out really nicely because our sine cancels out and our cosines turn into u's. So we have u squared minus u to the 4th du all multiplied by negative 1024. And once that goes in, we have these, the integral of that. And after that, we can replace our u's with cosine thetas. And once all that's done, we have to finally replace this cosine theta with our actual value for x, because we want this to be in terms of x. And for that, we just go back to what we have here. Cosine theta is equal to root 16 minus x squared all divided by 4, and plug that in to get our final answer. So partial fraction decomposition isn't so much an actual method of integration as it is a method to make our integration easier and doable. So basically what it entails is breaking up fractions into things that we know how to integrate. We're looking for factorable denominators, and once we're done, the integration should mostly turn into natural logs. So the example that we're going to use here is the integral of 1 over 4x squared minus 4x minus 8. And once we factor out a quarter from all of that, and we begin to break it up into doable things, right? We have our doable denominator, x minus 2 and x plus 1. We can break that into 2 different fractions with a and b on top. If we multiply through to get a common denominator, all of that is going to be equal to what's on top, which is 1. From that, we can create a system of equations. And from that system of equations, we can go through and solve and have b equal negative 1/3 and a equals 1/3. After that, we have 2 separate fractions, right? We have the integral of 1/3 divided by x minus 2 minus 1/3 divided by x plus 1. And that's much easier to take the integral of. And so we have 1/3 natural log of the absolute value of x minus 2 minus 1/3 natural log of absolute value x plus 1. So our next topic that we're going to cover is improper integrals, and that deals with areas involving asymptotes and infinite domains. What we use here is to use limits to check and find what the actual integral will be. So for our first example right here, we have the integral from infinity to e of 1 over x ln x squared dx. And what we do first, we change the limit to t as t approaches infinity. And then we can use like a simple u sub, let u equal ln of x, du equals 1 over x dx. That cancels out very nicely. We have ln of t on top, 1 on the bottom. Limit as t approaches infinity of this integral, 1 over u squared. And after that, we can just go straight into negative 1 over u from ln t to 1 as t approaches infinity. And then basically we just go through that, 1 over ln t and 1 over 1. We end up getting 1. Our next and final topic is arc length, which is the way to find the length of a curve. It often requires many of the methods that we just learned. This is the formula right here. Length equals the integral from b to a of the square root of 1 plus dy over dx squared dx. So this is kind of a culmination of everything that we've learned so far. What we want to do is find the length of the curve on the interval from 0 to 3, and f prime of x equals e to the x, and that means that 1 plus f prime of x squared is equal to 1 plus e to the 2x, and we have the integral from 3 to 0 for x, and we have 1 plus e to the 2x dx all square rooted. We have u equal e to the x, du equal e to the x dx, du by extension then equals u dx, right, because we can substitute that in. And that means du over u equals dx. We can plug that in and get our new integral right here, e cubed to 1 square root of 1 plus u squared divided by u du. After that, we're looking for a trig substitution, which we've done before. We have u equal to tan theta, du equal to secant squared theta, and secant theta equals square root of 1 plus u squared. And convert this into trig. See, our boundary has changed again to adapt to this new trig. We have from the tangent inverse of e cubed to pi over 4, the integral of secant theta divided by tangent theta times secant squared theta d theta. And from this, we can keep going and we can square the tangent on the bottom and also add a tangent on top. And that makes us in a position where we're able to use trig identities to have secant squared minus 1 replace the tangent squared of x. We have secant squared times secant theta tangent theta d theta. From here, we use another substitution. We have v equals secant theta, dv equals secant theta tangent theta, and that cancels out very nicely with what we have. And we have the integral of v squared divided by v squared minus 1 dv. So since we've once again changed the variable in our integral, we have to also change the boundaries. So what we do is we plug all this in, we get the square root of 1 plus e to the 6th as our top bound and our bottom bound as root 2. And from here we can say that v squared minus 1 plus 1 divided by v squared minus 1, which is the same as what we had before. And this can simplify to 1 plus 1 over v squared minus 1. And from here, we do partial fraction decomposition by getting v plus 1 and v minus 1 on the bottom. A and our b, we go through and solve. B equals negative 1/2, a equals 1/2. And we plug this back into our integral to get 1 plus 1/2 divided by v minus 1 minus 1/2 divided by v plus 1. And once we are able to take the integral of that, we end up with v plus 1/2 natural log of v minus 1 minus 1/2 natural log of v plus 1 on the interval of square root of 1 plus e to the 6th to root 2. And basically we plug all that in and we crunch some numbers, and our final answer ends up being negative 1/2 natural log of root 2 minus 1 divided by root 2 plus 1. So some common mistakes that people make during these: they often forget to keep track of limits, so we need to make sure that we're always being very vigilant and making sure nothing's getting lost in our math. We have to check to make sure the integral is proper or improper. We have to make sure that we're actually answering what the question is asking us. We need to be neat and organized. As you can see, it's very, very easy to make a mistake and miss a number, miss a negative somewhere along the road. It's very important to stay focused and persevere. And That's what we've got for you today. Thank you for watching.